Periodic trends has always been one of my most favorite parts of chemistry, so I'm so excited to walk you through the periodic table, unlock even more of its secrets, and learn about the trends that govern the way elements react with each other and with their environment. When we talk about these trends, the take home that we have is we gain three tools by which we compare elements to each other: atomic size, ionization energy, and electron affinity. When we talked about quantum numbers, for each shell of n, we got an additional subshell available to us. As we move down the periodic table, we get another value of n. So for each additional level of the periodic table, we get another layer of electrons, and in some cases, we even get a larger number of electrons. Each additional n layer is like adding another layer of clothing. If the nucleus is the body of the atom, n equals 1, 2 is the underwear, n equals 2 is the long underwear, for warmth of course, n equals 3 is a normal set of clothes, n equals 4 is a sweatshirt and sweatpants, n equals 5 is a coat, n equals 6 is a windbreaker, n equals 7 is one of those hideous disposable plastic ponchos to protect for the weather, just in case it rains. I don't know about you, but every time I add a layer of clothing, my radius increases. The same is true for atoms. As you progress down the periodic table from hydrogen to cesium, the atomic radius of the atom increases as n increases. For comparison, the radius of hydrogen is 37 picometers, while the radius of cesium is almost 10 times as large at 268 picometers. However, that's not the whole story. As we proceed from left across a period to right, so from neon or lithium or hydrogen to cesium, so from neon to lithium or radon to cesium, the atomic radius of the atom also increases. This change may be less intuitive, but it has a logical explanation. Remember the effective nuclear charge, or Z effective, which we talked about way back in 3.8 and 3.9? It turns out that not all electrons are treated the same by the nucleus. The inner, or core electrons, take the brunt of the charge-charge attraction from the nucleus. They shield the outer or valence electrons from the charge-charge attraction forces of the nucleus, so those outer electrons only feel a fraction of the nucleus's charge, or Z, hence the effective and Z effective. We quantify Z effective by adding the charge of the core electrons, which is negative, and therefore negates the charge of the nucleus, which is positive. Last time, we learned how the Z effective contributes to the energy of atomic orbitals and how that would affect the order in which orbitals are filled. Higher n values of s and p orbitals especially penetrate into the lower energy level orbitals, and the proximity of that electron density causes those orbitals to have a lower energy than other electrons in that n level. It turns out that in addition to influencing the energy of atomic orbitals and therefore the filling order of these orbitals, the Z effective influences the size of atoms too. So why do the elements get smaller as we go from left to right? Well, if we look at a single n level on the periodic table, lithium to neon, the Z, or charge of the nucleus, increases, so from plus 3 to plus 10, but the charge from the core electrons does not change. Remember, so in this case, both of these elements have two core electrons that correspond to the electrons in the 1s orbital. Therefore, as you add more and more protons, but keep the number of core electrons constant, the valence electrons are going to feel the pull of the nucleus more and more with each proton added. So, as we add protons and increase the Z effective across a period, the atomic radius will decrease from left to right. We see this here with lithium and neon. So both lithium and neon have two core electrons, but the nucleus charge of lithium is plus 3, whereas it's plus 10 for neon. So the effective charge of neon is plus 8 compared to a charge of lithium. So those 6 valence electrons in neon will feel a +8 charge compared to a +1 charge for the 1 electron in lithium. So therefore, even though there are more electrons in the n equals 2, neon will be smaller because that larger effective nuclear charge will pull those electrons in more tightly, and therefore the atom will be smaller. If we map this trend on a periodic table, the atomic radius increases as we go from right to left across a period because we decrease the number of protons in the same n level, but keep the core electrons constant and therefore decrease the Z effective. And as we move down a group, because we add more layers of electron density. Elements in the periodic table also have the ability to gain and lose electrons. Since the addition of electrons changes the radius of an element, we can understand how the formation of anions and cations would change the size of an atom. Generally speaking, the formation of cations, or positively charged ions in which electrons are lost, the atom becomes smaller. So lithium atom is twice as large as lithium plus. On the other hand, when you add electrons to an anion, the radius of the ion will increase. So O2 minus is larger than oxygen. We can see here this is a map that visually demonstrates the relative size of the atoms. So our largest element, cesium, is in the bottom left-hand corner, whereas our smallest element, helium, is in the top right. The next tool in our toolkit is the ionization energy, or the IE. Ionization energy is defined as the energy needed to remove 1 mole of electrons from 1 mole of gas phase atoms or ions in their ground states. Do you remember when we talked about work functions, or the amount of energy needed to dislodge an electron from an atom? This is a similar idea, except the formalism is that the ionization energy is in terms of 1 mole of each and in the gas phase. Either way, the ionization energy is the energy that we need to pump into an atom to remove a valence electron. Remember our sign convention for energy changes. Ionization energies are generally positive, which means energy needs to be absorbed by the atom to release the electron. The larger the IE, the more energy is needed, and therefore it is harder for the atom to give up the electron. Or as I like to think of it, those atoms don't want to release the electrons, at least not without a steep price to pay. The important thing to remember for ionization energy, and later for electron affinity, that can help us rationalize these trends if you ever get stuck, is that every atom is trying to achieve the enviable noble gas configuration, or to have an S2P6 on their outer shell. Noble gases are the it elements of the periodic table. Everyone, or at least everyone in the S and P blocks, wants to be like them. Whether or not adding or gaining an electron will help an element achieve noble gas configuration can help justify or reverse explain a comparison of ionization energies or electron affinities for a set group of atoms. We don't have a nice formula to predict the ionization energy for the elements like Bohr was able to calculate for a single electron system, because it turns out that multi-electron systems are very, very complicated, much like humans are. However, there have been generations of scientists who have done their experiments to empirically or experimentally determine what the ionization energy is for each element. Ionization energy, like atomic radius, is related to the Z effective. The larger the pull that the nucleus has on those outer shell electrons, or the larger the magnitude of the Z effective, the more energy will be needed to pump into those atoms to release those electrons. Therefore, the ionization energy will increase. So the more tightly those electrons are held on by the nucleus due to the increased Z effective, the higher the ionization energy will be. The element with the highest Z effective is helium, followed closely by neon. This makes sense for helium because it has only 2 core electrons, which also happen to be the outer electrons. Neon is the highest Z effective of any element of its row, and only has 1 row of core electrons, of which there are only 2. So, ionization energy, as we saw in the previous discussion with the atomic radius, tracks the Z effective. It increases from left to right as the number of protons increase, while N does not, and it increases up the table as you decrease the number of N levels that shield the valence electrons. Or, as I like to think of it, with ionization energy, all roads point to helium. This is opposed to atomic radius, where all roads point to cesium. Now, there are 2 anomalies in this trend. The first is between groups 2 and 13, or the point where electrons are lost from a p orbital rather than an s orbital. This is because p orbitals have a lower Z effective than s orbitals due to the fact that s orbitals have electron density closer to the nucleus as they interpenetrate the 1s orbital, and therefore, because p orbitals are not pulled on as heavily or have a lower Z effective than s orbitals, they take less energy to remove. The other exception is between groups 16 and 17, or between nitrogen and oxygen. This is because oxygen has 1 paired set of electrons in its p orbital. Paired electrons exhibit electron repulsions, which raises the energy of the orbital. Turns out that oxygen is more stable as it has a lower energy when it gives up an electron than when it has that electron because the electron repulsions are removed. So oxygen is more stable when it's has a positive charge than when it's neutral. Therefore, it takes less energy to remove an electron from oxygen than its neighbor nitrogen, which does not have any paired p electrons and therefore is perfectly happy in its neutral state. Atoms can have multiple ionization energies, depending on how many valence electrons are available. Generally, ionization energies increase as you remove subsequent electrons. This is because as you remove more and more electrons, you get closer to the nucleus, have fewer electrons shielding the charge, which results in a higher Z effective. And because of the higher Z effective, the nucleus is pulling on those electrons more strongly, so therefore a higher energy input is needed to overcome that strong pull of the nucleus. The last tool is electron affinity, or EA, which is the energy change that occurs when 1 mole of electrons is added to 1 mole of atoms or ions in the gas phase. Or it tells us how likely an atom is to accept an electron. In this case, both the sign and magnitude of the EA can tell us how likely an atom or ion is to accept an electron. A negative sign on the EA means that the energy is released or lost when an electron is added. This indicates that the atom, which has the charge-charge attractions between the nucleus and electron, has a lower energy or is more stable than before the electron was added. Or atoms or ions with a bigger, more negative value for IE are more likely to accept electrons. This is in comparison or in contrast to atoms or ions with a positive value. These atoms have a higher energy or are less stable after the addition of an electron, and therefore are not likely to accept that electron. The halogens have the highest electron affinities in their period. This is because halogens, which are already 1 electron away from looking like a noble gas, are going to readily accept an electron to fill that p orbital, and therefore will have a very large negative ionization energy. An element like beryllium, however, has an ionization energy that is greater than 0 because adding an electron would require it to fill another orbital, the p orbital, which has a higher energy than an s orbital. Also consistently having values that are positive are the noble gases. because the noble gases don't have any motivation to accept an electron. There is no energetic benefit. In fact, there's an energetic penalty because they are already in noble gas configuration. Unfortunately, aside from the halogens, for the noble gases being positive and group 2 generally being less negative than group 1, the trends for electron affinity are not as straightforward as ionization energy and atomic radius. Generally speaking, the electron affinity increases or becomes more negative as we move from left to right across a period. However, whether or not an electron would help an atom reach noble gas configuration or make the atom have a higher or lower energy can help you rationalize the differences between atoms. Specifically, you can consider atoms within rows in the p and s blocks. So when you're talking about atomic trends, just remember, for ionization and energy and electron affinity, will adding or subtracting an electron make the element look more like a noble gas? For atomic radius, what happens when I add an extra layer of electrons? What happens to the number of core electrons and number of protons as we go across a period? Specifically, what happens to the Z effective and how does that affect the size of the electron? We're also really concerned with how the Z effective tracks with the ionization energy and electron affinity. I hope you've enjoyed learning about periodic trends. We'll practice using our toolkit and comparing elements in class.